Alright, in this video, I will talk about limits. It's a topic that I've been avoiding for a particular reason. And it is because we do this thing called L'Hôpital's rule. It's a French name that means hospital, but it's a name. So someone was named hospital for some reason. But he did some work with limits, and I'll just show you what it is. If you take some limit and the top and bottom approach 0 or infinity, they both have to approach either 0 or they both have to approach some kind of infinity. It could be positive or negative. But if they both do that, then the limit of this is equal to the limit of the derivative of the top and derivative of bottom. Now, I'd go into more detail on this, but I want to actually get somewhere with this. So, here, just quick introduction on L'Hôpital. Just before we even get to limits. So L'Hôpital he wrote a book. And in that book, he utilized this concept that he was shown, called, and I'm resisting calling it L'Hôpital's rule before he even wrote the book, but during this period of time, he found out this fact from someone else, and so he's like, okay, I'm going to put this in a math book. And by the way, math books were just as important as any other book during this time period. And by the way, this is like, I believe it's right about 1670 or maybe 1669. But about this year, I'll say circa or something like that, he wrote a math book, and in it he put this limit idea. All right. Just know it's an idea. We're going to go into it, so don't worry about what it's saying. And yeah, into a book. And now it's called L'Hôpital's rule. Yay. L'Hôpital's rule. Though, who actually discovered it? That is kind of unknown. What we usually give credit to is this guy named Bernoulli. And I forget what Bernoulli. I'm probably spelling this wrong. So there's a family of Bernoullis. They discovered all sorts of things like water pressure. They have another guy in this family discovered like this thing to do with. They're famous in mathematics for coming up with problems in the mathematical world, like what is this number E? One of those Bernoullis found it and was like, okay, there has to be something special about this. Another one had this question called like, was 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared going to infinity? And turns out that's equal pi squared over 6. They didn't solve that, but they came up with a problem called the Basel problem. That was another Bernoulli. I said water pressure, so that's something you might find. Another thing is binomial coefficients. They did some work there, and there's this really famous formula that connects all kind of additions of these kind of things. There's a formula that solves them. But either way, that's the Bernoullis. It's a family. There's a Jacob, there's a John Bernoulli, there's a Nicholas Bernoulli, there's more Bernoullis where that came from. Very famous family in mathematics and really science in general during this period of time. And I would say most of their work was 1660s to, I'd say, about 1710s. And then they kind of fell out of vogue. But either way. So Bernoulli's discovered this idea of differential calculus from Leibniz and Newton. They brought it into the world, and what they did is I believe they messed with some problems for a bit, and then they showed this L'Hôpital guy, and I believe this is all in France at the period of time, or the area of France. And then L'Hôpital wrote a math book and put it in it. And it's just this cool little fact that you could solve a limit using derivatives, which is interesting because a derivative is a kind of limit, and we'll look into that. So that's Bernoulli's and L'Hôpital. L'Hôpital is just a guy who wrote a math book. But why do we care about this little bit of information? Well, here we go. Oops, drew on this desk. All right. So what is a limit? That's what we're going to talk about on the other side of this page. That's so sloppy. That's awesome. So limits, they weren't heavily... Man, actually, I don't know the beginning of limits too well. But I'll tell you right now, it's really an 1800s concept. So it's kind of weird that this rule was kind of found out. So my idea is that limits were probably something to do with just like it's really an algebraic way to talk about things that shouldn't happen. All right, that's what I think limits are for. If something happens in algebra where it ruins a problem, limits get around that and they can give you results for things. And what do I mean? Here, let's talk about this is one of the most famous L'Hopital problems, or at least my favorite. Let's say that's equal to f of x. All right, just so we can mess with it, utilize it. So let's graph some axes. So this function, interesting enough, looks like this. All right, it starts at 1 in the middle, and it's at 0. It equals 1. Then it kind of does that sine shape. They get smaller and smaller because it's a wave. That's divided by x, right? There's your x line. So if you divide by more negative and negative x's, then it just keeps on going down. Same goes for the positive side. It just oscillates and then gets smaller and smaller. So it basically finds out to 0. So there's kind of two interesting problems here. What does it approach at infinity? Like what value? Of course, it approaches 0. You can see it on the curve. And what does it approach at 0? That is what we actually care about here. And it approaches 1. All right, you can see that on the curve. It's not very trivial. Until you start asking the question, wait, why is it 1? Because, hey, if I plug in 0 here, sine of 0, we know that to be 0. And if x is 0, we know that to be 0. 0 over 0 is what we call, again, as indeterminate, meaning it has infinite or no defined answer. And so getting infinite 0 over 0 is a problem. And also another problem would be infinity over infinity or negative infinity over negative infinity. It doesn't matter as long as there's infinity on top and bottom. That's another indeterminate form that happens a lot. And limits reconcile these. They're like it's just a algebraic tool to get around all of these problems that mathematics gives us. Maybe a popular one is x over x. All right, so this is what we're going to say. We're going to say x over x, and the limit as x approaches 0. All right? If you plug in 0, you get 0 over 0. No solution yet. However, we can work with this. What's x divided by x? That is 1. Easy. And so if this equals 1, what's the limit as x approaches 0? Well, if you plug in x equals anything here, it's just 1. And so if you were to graph this as a curve, it's going to be a flat line at 1, right? Except we have what we call a hole, or man, there's another name for it, but whatever. It's a hole in the function at 0 because you get that 0 over 0. And the limit is an innovation, so we don't have to keep talking about that hole as a hole. We can just say, okay, the limit at that point is 1. So we don't have to be ridiculous and say that, yeah, it doesn't exist at this point for some reason. We can say that if we approach it from both sides, and that is actually how the limit is defined, approaching from both sides, we get 1. So another way to think of a limit is if you draw a curve, it is that point on the curve that connects the line. All right, sometimes that point doesn't exist and you get a hole. Sometimes it's actually on the line. So if you take x over x, what's the limit as, forget that I wrote that equal sign, what's the limit as x approaches 5 of x over x? Well, plug in 5, 5 divided by 5 is 1. And guess what? It's solved. And I didn't have to do simplification here. I just plugged in 5 over 5, right? So that's another way. And those are not those are, I believe the word here is trivial. And by the way, that wouldn't be 5 on the curve, just from how I drew sine. Ignore that. But that's the important concept here. That you can get past algebraic problems. Alright? Now, I'll tell you right now, the vast amount of algebraic problems don't require limits. And so I think for that reason, it's actually ridiculous that we teach limits as a not calculus concept, because L'Hopital's rule, we already saw that it requires a derivative somewhere along the line. And so the fact that we teach, I mean, derivative is kind of limit, but you need derivatives to solve some limits, and so it's kind of ridiculous that we introduce it in pre-calculus so often and stuff like that. Now, if you've never seen a limit before, don't worry about it. All it is, it's approaching a value. And there's other ways to solve limits, like that sine x over x. You don't have to, y is equal 1? Well, we can reconcile that by picking a point that's really close to 0, but not 0. And I'll tell you this. Let's do sine of 0.001. I'll tell you right now, that is really close to 0.001. So we're just going to put squiggly. It's about 0.001. Interesting enough. And that makes sense because it's sine of 0, 0, so that approximate that. And then, guess what x is when it's 0.01? 001 is 0.001. That's nothing to it. And so if you divide these two results, all right, 0.001 divided by 0.001, because it's, I put squigglies here, I'll put another set of squigglies. Why am I calling them squigglies? That's so unprofessional. You get 1. So that is a way to make sense of this result of 1. Because if you take a point really close to 0, that is really close to 0, then you get basically the value at 0. And so that is one way of solving limits. But let's finish this video with algebraic methods, all right? This is what they teach in pre-calculus, but let's do one with square roots and one with just factoring. All right. Oh, this is my last sheet here. All right. So we're going to finish up with some limits. So let's just practice. So what is the limit as x approaches 2 of x squared? Plug it in. If it doesn't work, then you have to do some special algebra, but you don't. Because plugging 2 here, 2 squared is 4. Done. Solved the limit. We're so happy. What's another limit? How about the limit as x approaches... let's see here. Let me think of a problem. How about this? I don't know. I like 5 right now, so I'm going to use 5. Let's say x minus 5 squared over x minus 5. Alright. What should be going off in your head is that, oh, this simplifies. This is just the same thing on top and same thing on bottom. And you're right, and that's how you'd solve this. X minus 5 squared divided by x minus 5. If this was x squared over x, then it just becomes x. So in this case, x minus 5 squared divided by x minus 5 is just x minus 5. It gets rid of one of the powers. All right? So limit as x approaches 5 still. And then plug in 5. 5 minus 5 is 0. So the limit here is 0. But if you plug in 5 from the get-go, which I skipped, just because if you plug in 5 minus 5 is 0, 5 minus 5 is 0. 0 is 0, indeterminate. That gets you nowhere. All right? So that's an algebraic method. However, when they give you this problem, know what they do? And I'm saying like just teachers and math books in general. They try to mess with you. Rather than write it out algebraic like this, like that's so clear, what they do is they expand out the top so it's not clear. So this is the same as x squared minus 2 5s, which is 10x. And then 5 times 5, that's 25. All right, over x minus 5. This is the same expression, but they wrote it out. So it's not clear that this is actually the exact same thing as the bottom squared. So that's an algebraic thing. There's other more complicated ones, but you get the idea. It's just a matter of factoring. So you have to see that, oh, you can break this apart and see what comes. I'll probably do some algebra videos where I actually try something like this so I can see how that turns into x minus 5 squared. But that's not part of this video. We just want to talk about limits. And let's do a square root kind of limit. All right, limit as x approaches, let's say 4. All right, so square root of x minus 2. You'll see how I came up with this in a bit. And then let's say 2x minus 8. All right, and this is how I came up with the problem, by the way. I came up with it because if you plug in 4 here, you get 0. And if you plug in 4 here, square root of 4 is 2. 2 minus 2 is 4, is 0. So you get 0, 0. So I actually manufactured this problem to get a problem. But if this was purely random, just picked out of the blue, odds are this would simplify easily and you could just plug in 4 and get a result. But because I chose it, I know it's going to be difficult. So we know we get 0, 0 because this becomes square root of 4. That's 2. And then this becomes 4 times 2, 8, minus 8, 0. So how do you solve this guy? It's actually kind of fun in my opinion. Let's rewrite what square root x minus 2 is. All right, let's switch colors to green. Square root x minus 2. All right, we're going to use a really interesting algebraic concept called a conjugate. So we know that multiplying any value by 1 changes nothing about that, right? It doesn't really change the problem because multiplying by 1 doesn't. However, sometimes it messes with the algebra a little bit. All right, and this is how you do it. So if ever you see a square root, actually before I even get to that, if we have a plus b times a minus b, what happens? And I'll let you try to solve that. So the problem with having a square root is that if there's a square root, you can't really simplify it. But how do you simplify a square root if it's just by itself? You want to square it, right? So we want to just square that square root, and that should simplify the problem a good deal. So let's see if we can do that by writing. Let's see if there's a way to do that. And the way, I'll tell you right now, is conjugates. Just write the positive. If it's negative, you're going to write the positive of the second value and multiply it. Or if it's positive here, you're going to write the negative. So if you multiply this, you'll find that a times a is a squared. You'll find that a times b, negative b, is, negative ab. You'll find that b times a is positive ab. And you'll find that b times negative b is negative b squared. And if you see here, these two guys cancel out. That's a negative AB and positive AB. So the cool thing about any conjugate, anything, A and B could be any number here, is it always becomes A squared minus B squared. That means if we do that to this, if we multiply that times square root of x plus 2, know what that'll do? That will square the first term and nothing else. Like, we won't have these terms, and so they just go away. And we want that to happen because we don't want to keep any square roots in the problem. We don't want to keep square root 2 times negative 2. So, but if we're going to multiply the top by that, we have to also multiply the bottom by it. So square root of x plus 2. Multiply that on bottom. So if you multiply that on top, we know just conjugate form. That's the first term squared. So square root of x squared is just x, right? Then negative 2 times plus 2 is negative 4. And on bottom, we have 2x minus 8. And let's just leave this in parentheses. Square root of x plus 2. Just checking for a second. If we plug in 4, we get... No, if we plug in 4, that still doesn't simplify. But we can do some... We still have one more trick up our sleeve. What's 2x minus 8? 2x, if you factor a 2, you have x minus 4 on top. Let's put that in parentheses. This is same as 2 times x and 2 times 4. So it's 2 times x and 2 times negative 4. And then we still have that square root of x plus 2 down here. So, guess what? Those two things cancel. Alright, and so we get 1 over 2 times square root of x plus 2. Alright, and now let's plug it in the limit. If we plug in 4 into this, 1 over, so square root of 4 is 2. 2 plus 2 is 4. 4 times 2 is 8. So you get 1 over 8. And I'll tell you right now, oh man, I should have brought a graphing calculator up here. But either way, if I were to graph it, this is the incredible result. If you have 4 on this equation, it actually simplifies perfectly to 1 over 8, even though you get 0 over 0 if you did others. So that's algebraic method. It's kind of fun in my opinion, but it's definitely not something you want to teach in pre-cal. Pre-cal should be, honestly, I don't think there should be a pre-cal. You should just jump right into calculus. Because you'll see in a second, derivatives actually make our lives easier, especially for problems like this. Alright, see you in the next video.